In this video, we're going to talk about solubility and complex ion equilibria. So back in chapter 13, we talked about equilibrium constants related to solutions. And in chapter 14, we talked about equilibrium constants related to acids and bases. So in this chapter, we're going to talk about complex ion equilibria, and we're going to talk about how that affects solubility. So, for example, if we take a saturated solution, in this case we're going to look at a saturated solution of calcium fluoride, and we have some solid calcium fluoride at the bottom of our container. So we get an equilibrium going between the solid calcium fluoride and the ions in solution. So a certain amount, if we add some calcium fluoride to water, a certain amount of that is going to break apart into calcium ions and fluoride ions. So we can write an equilibrium constant for this. And remember that we don't include solids in the equilibrium constant expression. So we can write an equilibrium expression for this if we write just the aqueous component, since we don't include solids. We would have calcium times fluorine, so the concentration of calcium times the concentration of fluorine squared, and we call this equilibrium constant KSP, since this relates to the solubility. So KSP is what we call the solubility product constant. It's an equilibrium expression that represents how much of an ionic solid will dissolve in water. So it's also called the solubility product. Now, the solubility equilibrium is not affected by any excess solid. So if we have excess solid, we're not going to have more of the whatever component we're dealing with dissolve in water. There's only so much of any ionic solid that will dissolve in water. And we're going to look at some of the different solubility constants for that. But once we've reached that limit, it doesn't matter if you have excess solid at the bottom of the container. You're still not going to be able to dissolve anymore because you've reached the solubility limit. It also is not affected by the size of the particles present. So you may have larger particles or you may have smaller particles, but that's not going to affect your equilibrium constant. The constant is only affected by the concentrations that are present in solution. So the solubility of a given solid and its solubility product. The solubility is an equilibrium position. So just like everything else, we're still going to have things going in both directions. We're still going to be forming some of the solid and forming some of the ions, but we're at equilibrium. The rate there is the same in each direction. Now, just like with other equilibrium constants, it will change with temperature. So some things are actually more soluble at higher temperatures. Some things are actually more soluble at lower temperatures. But the solubility product is specific to that temperature. If you change the temperature, you change the solubility product. So let's look at an example of calculating a solubility product. If the concentrations of calcium and fluorine in a saturated solution of calcium fluoride are known, we want to calculate KSP. So we've already written the equilibrium expression for this equation, but we'll write it here again. So KSP would be equal to the concentration of the calcium ion times the concentration of the fluoride ion. And since the fluoride ion has a coefficient of 2, this would be squared. So if we plug in the concentration of calcium, which is 3.3 times 10 to the negative fourth, and fluorine, which is 6.7 times 10 to the negative fourth, and we're going to square that. So if you type into your calculator 3.3 times 10 to the negative fourth times 6.7 times 10 to the negative fourth squared, so this entire quantity here is squared, you should come up with 1.5 times 10 to the negative 10th. So all of your equilibrium constants, Kc, Ka, Kb, Ksp, anything that is an equilibrium constant is unitless. So we would not include units for this. So let's look at another example. Calculate the Ksp value for bismuth sulfide, which has a solubility of 1 times 10 to the negative 15th moles per liter at 25 degrees Celsius. So in this case, we first have to write the equation because it's not given to us. Bismuth sulfide, when it dissolves in solution, so bismuth sulfide is going to be a solid. So we're going to get bismuth and we're going to get sulfur. Now we need to put charges and we need to put the coefficients. So bismuth is one of our post-transition metals. It's next to lead. So we need to determine the charge on bismuth. So sulfur has a 2 negative charge on it, and there are 3 of them, which is a total of 6 negative, which means that since there are 2 bismuths, each one has to have a 3 positive charge. So we have 2 bismuths with a 3 positive charge and 3 sulfurs with a 2 negative charge on them. And these would be aqueous. So, since there are 2 of the bismuths and 3 of the sulfurs, we need to calculate the Ksp here. But first, we have to calculate the concentration of bismuth and of sulfur. So bismuth, actually let's switch colors here. We have a solubility of 1 times 10 to the negative 5th moles per liter, so moles per liter is molarity. So the concentration of bismuth is going to be 2 times that, since there are 2 bismuth ions. So we're going to have 2 times 1.0 times 10 to the negative 15. And if you multiply that out, that comes out to 2.0 times 10 to the negative 15th. And for sulfur, we're going to have 3 times concentration, since there are 3 of them. So we're going to have 3.0 times 10 to the negative 15th molar. So if we write Ksp for this, so Ksp would be the concentration of bismuth squared, since there are 2 of them, times the concentration of sulfur cubed, since there are 3 of them. So if we plug in the concentration that we came up with for bismuth and the concentration that we came up with for sulfur, if you take 2.0 times 10 to the negative 15 squared times 3.0 times 10 to the negative 15 cubed, you should come up with 1.1 times 10 to the negative 73 for your solubility. So it's a pretty low number, which means that bismuth sulfide is not going to be very soluble in solution. So let's take a look at one more example here. Approximately 0.14 grams of nickel hydroxide dissolves per liter of water at 20 degrees Celsius. Calculate KSP for nickel hydroxide at this temperature. So if we have nickel hydroxide in solution, let's get rid of that there. So nickel hydroxide is a solid. Nickel is one of our transition metals. So hydroxide has a negative charge on it, and there are two of them, which means that nickel would have a 2 positive. So we're going to have Ni2 plus aqueous plus 2 of the hydroxide ions, which are also going to be aqueous. So this time we're given grams, and we're told that that will dissolve in 1 liter of water. So to calculate concentrations in order to plug into our expression for KSP, we're going to have to convert grams to moles and calculate the concentration. So if we have 0.14 grams of nickel hydroxide, and if you calculate the molar mass of nickel hydroxide, it comes out to 92.71 grams of nickel hydroxide. Per 1 mole of nickel hydroxide. So if we take 0.14, divide that by 92.71, we get 0.0015 moles of nickel hydroxide. And if we dissolve that 0.015 moles of nickel hydroxide in 1 liter, well, that's going to be 0.0015 mole. So if we write our expression for KSP, KSP is going to be equal to the concentration of nickel times the concentration of the hydroxide ion squared. Now, just like with the last one, there's only one nickel ion, so this is going to be the concentration of nickel, but we have to multiply this by 2 for the hydroxide ion, since there are 2 of them. So the concentration of the hydroxide ion is going to be 0.030 molar. So if we plug in 0.0015 for the nickel and 0.0030 squared for hydroxide, if you take 0.0015 times 0.0030 squared, you should come up with 1.4 times 10 to the negative 8th for the value for KSP. So this is a table here that shows some KSP values for some ionic compounds. So there's a table like this, usually in the appendix or the front cover of your textbook, and you can find KSP values, tables of those, on things like the NIST website, which has tables of standard values. So it's the National Institute, and I forget what the ST, National Institute of Science and Technology, I think. But There are websites like this that are reputable that contain KSP values and other constants. So let's take a look at an example where we have KSP and we have to calculate the molar solubility of the ions. So in this case, we want to calculate the molar solubility of magnesium fluoride. So we have the equilibrium part of our ice table. So remember when we had our ice table, we had the initial concentration, the change in concentration, and the equilibrium concentration. Well, we really only need to write equilibrium here, because if we just added magnesium fluoride to our water, our initial concentration is going to be 0. So you could write that part of the table if you want to, but we know at equilibrium, we're going to have formed some concentration of magnesium, and since we get 2 fluoride ions for every magnesium ion, the concentration of fluoride is going to be 2 times that of magnesium. So we know at equilibrium, our concentration of magnesium is going to be X, and our concentration of fluoride is going to be 2X. And we're given KSP here. So if we write our KSP expression, we have KSP is equal to the concentration of the magnesium ion times the concentration of the fluoride ion squared. So then we can plug in what we know. 7.4 times 10 to the negative 11 is equal to, we represented magnesium as X and fluorine is 2X. So if we go ahead and square the 2X, so we're going to work this out algebraically. So we have X, 2 squared is 4, and X squared is X squared. Then if we multiply the X times 4X squared, we get equals 4X cubed. And then we're going to divide both sides by 4. So we get that X cubed is equal to 1.85 times 10 to the negative 11th. And then we can take the cube root of that. So you may have to go into a menu on your calculator to find how to do the cubed root. So in TI-83s and TI-84s, it's usually under the math menu. If you're using one of the smaller TI-30s, then there should be a button to do a root to a different value, and then you would have to type in the value. So if you take the cube root here, you get 2.64 times 10 to the negative 4th molar for the molar solubility here. Okay, let's look at another example. We want to calculate KSP. Well, we have KSP. We want to calculate the molar solubility for copper iodate. So if we write the equilibrium expression for this, CuIO3 2. So iodate has a negative charge and there are 2 of them, which means that copper has a 2 positive charge on it. So we're going to have copper 2 positive plus 2 of the iodate ions in solution. So we would represent at equilibrium, we would represent copper as X, and we would represent the iodate ion as 2X. So we can write KSP is equal to the concentration of the copper ion times the concentration of the iodate ion squared. So we know KSP here, which is 1.4 times 10 to the negative 7th. And we're going to plug in the value for the value for the copper ion and the value for the iodate ion. So we have 1.4 times 10 to the negative 7th. And if we multiply this expression, we're going to get 4x squared. We multiply that by x, so we're going to get 4x cubed here. So if we divide this by 4, we get that x cubed, and I'm going to draw a line here just so that what I have on one side doesn't run into the other side. So we get x cubed is equal to 3.5 times 10 to the negative 8th. And if we take the cube root of this, we get x is equal to 3.3 times 10 to the negative 3rd molar. So we have two more examples here, and I'm going to let you work these through on your own and come up with the molar solubility for each one of these.